Hello and welcome to the next lesson in thermodynamics, and this one is on the Born Haber cycles, which are used to work out our enthalpy changes. As usual, here are our learning objectives, and we just have two. First of which is we have to understand what a Born Haber cycle is and how to use one to calculate the enthalpy changes from experimental data. That's number one. And then we have to consider these theoretical lattice enthalpies and how they're often quite different from experimental values. We have to understand why. Now, as we said before, we can't calculate lattice enthalpies directly, and we need to do it using a Born Haber cycle, which involves a few different steps, each of which is provided by an experiment. Okay, so what we're going to do is we're going to have a look at Born Haber cycle in order to calculate the lattice enthalpy of sodium chloride. So you'll remember from the definitions in a previous lesson that what we're talking about here is we're talking about sodium ions that are in the gaseous state reacting with the chloride ions also in the gaseous state to make 1 mole of sodium chloride as a solid. Okay, so that is written in this direction, that is the lattice enthalpy of formation of sodium chloride. And so that's what we're going to use the Born Haber cycle to work out. And a Born Haber cycle uses energy levels, where this particular level, for example, we're going to say that is the energy level that sodium ions in the gaseous state and chloride ions in the gaseous state, we're going to say that that is their energy level. And we're going to say that sodium chloride is on an energy level down here. So let's write sodium chloride solid like this. And so when we start with sodium ions and chloride ions, and we make sodium chloride solid, we know that we're going to get heat given out as an exothermic reaction. All right, so just like in the GCSE energy level diagrams, exothermic energy out direction is downwards. And so what you can see, if you think for a second, you can see that this delta H, this enthalpy change, is in fact the lattice enthalpy of formation of sodium chloride. And that's what we want to know, and we don't know that, and that's what we want to know. And so we're going to use this, we're going to develop this diagram in order to find it out. Now, from year 12, you'll remember a slightly different definition of an enthalpy of formation. So in year 12, our enthalpy of formation started off with elements in their standard states, didn't it, when we were doing Haber cycles. So in the standard state, a sodium ion, right, is solid, and a chlorine exists as a Cl2 molecule in the gaseous state. So that is their standard state. And let's say they have an energy level like that. And so this difference in energy is the normal enthalpy of formation. And you can look up that, it's quite easy to find in an experiment, but for sodium chloride that's minus 411 kilojoules per mole. So just notice while we're here that these two enthalpies of formation are different. The one we started with on the right hand side of the slide there is the lattice enthalpy of formation, starting off with gaseous ions, whereas the enthalpy of formation that we're familiar with from year 12 is the standard enthalpy of formation, where you start off with the elements in their standard states. solid sodium atoms and chlorine molecules, gaseous chlorine molecules. Okay, and the normal enthalpy of formation, we know that to be minus 411 kilojoules per mole. Okay, starting from there, we can then take the solid sodium and the gaseous chlorine molecules, and the first thing we can do is we can atomize those chlorine molecules. So you would get a chlorine atom in the gaseous state. Right, we've not done anything to the sodium yet, so that's still sodium solid. Right, but what we've done is we've gone from here to here on our chlorine, and we're going to say that we've had to put energy in. We've broken some bonds, so we've had to put energy in. That's endothermic, and so we're going to go upwards, and so that energy there is the atomization enthalpy. And in this case it's of chlorine. And that is, let's just change colour for now. That is we're putting energy in, and that is plus 122 kilojoules per mole. So what we've done is we've atomized that chlorine molecule to give us 1 mole of chlorine atoms from half a mole of chlorine molecules. And the next thing, of course, is we have to get our sodium atomized. All right, so we're going to have to put energy in to do that. All right, so our chlorine is going to be the same. We're not doing anything to our chlorine yet, but we're going to atomize our sodium. And make it in the gaseous state. Right, so we've gone from here to here, and we're going to say that is on this energy level here. And so again, we've put energy in so that our arrow goes upwards, and this is the atomization enthalpy. In this case of sodium. And switching back to red, I'm going to tell you that that is experimentally determined as 107 kilojoules per mole. Okay, so now we've got gaseous sodium atoms and gaseous chlorine atoms, and what we have to do now is we have to ionize them, don't we? So to ionize a sodium atom, so we're going to take sodium, deal with sodium first. To ionize a sodium atom into a sodium ion requires a little bit of energy, not much because it doesn't want its outer electron very much, but it still requires a bit of energy, and we're not doing anything to our so we take off that electron, we're not doing anything to our chlorine atom yet. All right, so we've added that energy in, so the energy level there we can draw like that, slightly above, and we can draw our arrow going upwards, reminding us that that is energy in, and that's going to be our first ionization energy of sodium, because we're just taking off 1 electron, and that electron, a mole of those electrons cost us 496 kilojoules per mole. So now, if you look at the top of the Born Haber cycle, we have sodium ions, and we've extracted some electrons from them, and we've got some chlorine gaseous atoms. So what we'll do is we'll just extend this along to the right hand side there. And now what we can do, let's just write the same things out again. We've got some sodium ions, we've got some electrons, and we've got some chlorine gaseous atoms. And then what we're going to do is we're going to let those chlorine atoms take those electrons such that the chlorine atoms are going to turn into chloride ions. And that's an exothermic process, and so that means that energy is going to come out, and so we can draw our arrow coming down, and that energy is known as the first electron affinity. So that's our first electron affinity of our chlorine. And as it happens, when chlorine gaseous atoms take electrons, then they give out they give out 396 kilojoules per mole of energy, and because that's giving out, we give it a minus sign. And so now, let's just go back here, write this in red. So now we have our Born Haber cycle. And at this stage, what we want to do is we want to remember our Hess's law from year 12. And I'm sure you remember that Hess's law says that it doesn't matter which way you go in a reaction, the enthalpy change is always the same. So we want the enthalpy change for going in this direction from sodium and chloride gaseous ions to give us sodium chloride solid. But that enthalpy change that we've got in green there is the same enthalpy change as if we go up this way and then all the way down. It's the same in the end. All right, so what we can do is we can write it out using the numbers that we know. If we're after our enthalpy change, our lattice enthalpy change of formation, then we can write it out longhand. So let me do that for you. So our enthalpy change, our lattice enthalpy change of formation, is going to be 396. So notice I've changed the sign, because if we're going in this direction up this arrow, we need to change this sign here. So it's 396. And then what we're doing now is we're going to come down this direction. So we have to subtract our 496, which was our first ionization of sodium. And then we're coming down in this direction again. So we have to subtract our 107. And same process here. We're going to come down for our atomization of chlorine. So we have to subtract our 122. And then we're going in this same direction for our enthalpy of formation. And so we're going in the same direction as the arrow, so we keep the sign of the energy change the same. So that's going to be a minus 411. And if you make all those additions and subtractions, and before we actually do that, I'm just going to correct a little error that I've made. So the first electron affinity of chlorine here is not minus 396, it's actually minus 349. So I have to correct this one as well. So when we do all that, it comes out at minus 787 kilojoules per mole. And that is the answer, which is our lattice enthalpy of formation of sodium chloride determined using our cycle. So very quickly, let's do another example, but this time let's use, instead of sodium from group 1, let's use magnesium from group 2. And the reason why I want to show you this example is because when magnesium makes magnesium chloride, for example, we get magnesium 2+ ions. Okay, so again, we're trying to find out the lattice enthalpy of formation of magnesium chloride. So let's start off halfway on our right hand side with our magnesium 2 plus ions, and our chloride ions, both in the gaseous state, right? But you'll know that the formula of magnesium chloride is MgCl2. So at the bottom, we're going to draw our MgCl2 solid, and that means that we need 2 chloride ions, and when those gaseous ions make magnesium chloride solid, that is our lattice enthalpy of formation of magnesium chloride. That's what we want, and we need to use this Born Haber cycle to find it out. And so the other thing we know is at standard conditions, magnesium is going to be solid, and our chlorine is going to be a chloride molecule, gaseous chloride molecule, and this time we don't need half because we need 2 chlorine atoms, and that's 1 chlorine molecule. And so when those standard state magnesium and chlorines make magnesium chloride, we know that that's the enthalpy change of formation of magnesium chloride, and we can work that out experimentally, and we're given that. Let's make that in red. So that's minus 642 kilojoules per mole for the enthalpy formation from standard conditions of magnesium chloride. Okay, so that's our starting point, and what we're going to do now is we're going to atomize our chlorine. Okay, so we're going to need to put energy into that. All right, so we're going to get 2 chlorine gaseous atoms that we can. That's the change we're going to make. We're going to have to put energy in, and that's our atomization enthalpy of chlorine, and we're doing that for 2 atoms. Okay, so it is 122 so energy in, so 122, and we're doing it for 2 atoms, so we have to multiply that by 2. So it is 244 kilojoules per mole of chlorine gaseous atoms. Okay, so, and our magnesium didn't change, so we're just going to put that in there as magnesium solid like it was. Okay, so our next change is, of course, to atomize our magnesium. So we're going to go from solid magnesium to gaseous magnesium, and our 2 chlorines are going to stay the same. So that's the energy level of those species, and again we have to put energy in to atomize our solid magnesium, and we've got 1 mole of magnesium atoms we're making there. All right, so we don't have to times it by 2 or anything, but that costs us 738 kilojoules per mole to atomize those magnesium ions, and so the next thing is we have to ionize them. So we're going to take this magnesium gaseous atom and we're going to make it into a magnesium plus ion. All right, and when we do that, we're going to get an electron, and we've not done anything to our 2 chlorines, so we just write them the same as they were there. That's at this energy level, and we've put energy in, so the arrow is in that direction. And our first ionization energy of magnesium is actually 738 kilojoules, because I wrote the wrong number down here. Our atomization energy was only 148 kilojoules per mole. And so here we are, we've got a mole of magnesium 1 plus ions, but of course we need magnesium 2 plus ions, so we're going to need to extract another electron, not doing anything to the chlorine, so the chlorines stay the same. All right, and so we're going to add more energy into the system, to take that second electron off, and that is a huge plus 1,451 kilojoules per mole. But now, at least, we have some magnesium 2+ ions. All right, so we're going to take our Born Haber cycle. We're going to extend it across to the right-hand side there. We can rewrite, just to make it slightly easier for us. We can rewrite what we've got. I'm not making any changes, so the energy level is the same. We've got our 2 chlorine gaseous atoms. And then, of course, what we're going to do is we're going to take those 2 moles of gaseous chlorine atoms, and we're going to let them take those electrons. Okay, so that is going to be the first electron affinity of chlorine, and that is an exothermic process. Those chlorine atoms like taking those electrons, and so they give out energy in that process. But of course they're 2 moles, right? So we multiply it by 2. Right, and the first electron affinity of chlorine is 349 kilojoules per mole. And now we've been all the way around our cycle. And so what we can do is we can work out our enthalpy, our lattice enthalpy of formation of magnesium chloride. Let's switch to green just to make it look different. So our lattice enthalpy of formation of magnesium chloride is now going to be, we're going to go around in the opposite direction. So we're going to go around in this direction here, which is the opposite direction to our arrow. So we have to change that sign. So we've got 2 times 349, and then next step is to go against this arrow. So we're going to subtract the 1451, and then we're going to do the same for the other ionization energy. So we're going to subtract another 738, and then we're going to go against that direction, so we're going to have to subtract our 148, and same again here, we're going to subtract our 244, but we're going with that arrow, and so we leave the sign the same, and so that is minus 642, and when we do all that, we get the lattice enthalpy of formation of magnesium chloride, which turns out to be minus 2,525 kilojoules per mole. QED. Okay, our last learning objective, if you remember, was to understand the difference between theoretical lattice enthalpies and experimental lattice enthalpies. And the first thing to think about is that when we're talking about experimental lattice enthalpies, they're the ones that we get from the Born Haber cycles, because each one of those steps in the Born Haber cycle comes from an experiment. And so the Born Haber cycle lattice enthalpy is really what's happening in reality. However, at the same time, we can do a theoretical calculation of what these lattice enthalpies should be according to a theory, or actually a model. So what you use is you use a model of ionic bonding, and the model of ionic bonding assumes a perfect ionic bond where the ions are both spherical, both the cation and the ion are perfectly spherical, and it's a 100% ionic bond. And if you make that assumption, you can calculate theoretical lattice enthalpies. And when you do so, you get some results like this. So these are the experimental values from the Born Haber cycle. And so for magnesium chloride, the first one, experimentally we see minus 2,526 kilojoules per mole, whereas the perfect ionic model, and i.e. the theoretical value, is only minus 2,326. So quite a big difference. So I'll just write that, quite a big difference there for magnesium chloride, whereas with sodium chloride it's 787, minus 787 for experimental values, and minus 766 from theory. So you can probably say these are quite similar. So what conclusions could we draw from that? Well, we could say straight away that the bonding in magnesium chloride, and in fact both of them, but especially magnesium chloride, is stronger in practice than theory would suggest, because you've got a more exothermic lattice enthalpy in reality than you would calculate from perfect ionic theory. And the same is true, but to a lesser extent, for sodium chloride. That's one conclusion you might draw from this data, and the other one is that that experimental values tend to be, at least in these two examples, and pretty much all other examples when you look at them, the experimental values are more exothermic than the theoretical values. Okay, so now we've noticed the bare facts, we have to explain why this is true. And so to do that, let's have a look at the perfect ionic model. So we have a circle with a plus in it that is representing our cation, and it's a perfect circle, or in 3D that would be a sphere, and our anion is a perfect sphere as well. And so that is what the perfect ionic theory assumes. But in practice, what happens is that the negative charge cloud around the anion gets attracted to the cation's positive charge. So that becomes slightly polarized, as you can see in that diagram, represented in that diagram there. And so you could say that in practice, let's actually write this down, in practice, which is what we've got on the right hand side here, in practice, few ionic bonds are perfectly ionic. Right, and this slight polarization that's happening with our negative charge cloud around our anion is called covalent character, because that anion is sharing some of its negative electron charge. So in practice, few ionic bonds are perfectly ionic. Right, many exhibit covalent character. That covalent character is illustrated by that negative charge cloud being attracted to the cation here. So if we look back at our table of magnesium and sodium chlorides, let's ask ourselves which of those bonds has the most covalent character. And so what we can see is our magnesium chloride, right, where the difference between theory and experimental is greatest, exhibits more covalent character than the sodium chloride in this particular example. So sodium chloride is, the ions in sodium chloride are more perfectly spherical than in magnesium chloride. And I would suggest the reason for that is in magnesium you've got a, in the magnesium ion you have a higher charge density. You have a 2+ ion and it's slightly smaller, and so that positive charge is more densely packed, and that is what draws some of the electrons to it more than with sodium with its 1+ charge and a similar size, slightly bigger size. Lastly, just review our learning objectives, make sure we've done what we set out to do. And firstly, we said we were going to understand what a Born Haber cycle is and calculate enthalpy changes. So we did that a couple of times. And secondly, we've just looked at why theoretical lattice enthalpies using the perfect ionic model are different from the experimental values that come from our Born Haber cycle. So we're done. I hope that was clear.